Hello, good afternoon, ladies and gentlemen. I am Aniket from Additive Technologies, and I will be your host for today's webinar. First of all, we thanks each and everyone for taking out time and joining the webinar, Revolutionizing Drone Manufacturing with Additive Manufacturing. Before we start our session today, I would like to give a brief introduction about EDS Technologies. So, EDS Technologies was incorporated in 1994 to focus on providing PLM solutions, implementation, and support. We are the largest technology solution provider in India and partner to Dassault System. We have served more than 2,000 customers and operate across 11 locations in India with our headquarters at Bangalore. We also have various strategic partnerships with world leaders like EOS and Optomec for additive manufacturing requirements, Humanetics for ergonomic solutions for automotive and aerospace industries, Technia for ensuring product data quality. For military simulations and training needs of aerospace and defense industry, we have MAC Technologies, Anselon, and AGM for visual simulations. We also have a strategic partnership with Esri for GIS and location analytics. With respect to EDA, we closely work with Synopsys. We had a dedicated sales and marketing and customer satisfaction team to address customers' PLM business and support requirement. Now we will move to our presentation. So before that, I would like to give a short brief about our speaker, Mr. Arun Kashyap. So Arun Kashyap is an MTech in design engineering with 9+ years of experience in design prototyping and additive manufacturing. He works as a technical manager for additive manufacturing technology at EDS. He is specialized in LPBF, DFAM, and rapid prototyping across automotive, aerospace, healthcare, and energy sector. His expertise drives 3D printing adoption, digital manufacturing workflow, and supply chain integration that helps industries accelerate product innovation and development with advanced additive manufacturing solutions. So over to you, Arun.
Thanks, Aniket. Welcome everyone once again. My name is Arun and I'll be taking you to the webinar today. This is the agenda for the webinar. We'll be understanding what is additive manufacturing and why it is useful for drone industry, what are different applications, parts, and whether it is for metal part or polymer part, we'll look into it, how we can solve the development portion and how we can solve the industrial challenges from the drone through our manufacturing solutions that we have through US. Then we'll look at the design for additive manufacturing concepts in 3D printing and what materials we have to offer in for both metal and polymer components used in the drone. And then we'll look at few case studies of the drone and we'll also see the cost analysis of the 3D printed parts. So the outcome of this webinar would be will be beneficial in terms of technical understanding of all our solutions that we are having from the 3D printing industry, and also the commercial understanding how it provides end-to-end business solutions to your applications. So we'll begin with the uh, additive manufacturing. So what's additive manufacturing? Basically, additive manufacturing is a digital method, a process to convert the digital data into the form of the physical models, and that data can have any amount of complexity with it. So the simple workflow of additive manufacturing is we have a CAD model, and then the first job is to process that model for the 3D printing, which is CAM programming, and we call it as slicing. So we have to slice the data into the layer forms, and those slice informations are sent to the respective printer that for the 3D printing technology, and the printer prints those informations in the layers, uh, and you get your model finally out of the printer. And depending on the final requirement, the tolerance or the functionality or the quality of the component, you can choose in the post processing. There are several post processing methods available to impart the functionality in the component. So that's a brief about the 3D printing, and we'll look into the applications of drones. So today, mostly the drones are seen in the applications field. In the day-to-day life is either the drone solves the problem of surveillances or security purpose, or in the defense, we see a lot of unmanned aerial vehicles and the other drones which carry the payload for attack or any other defensive purposes. So there are defense drones, and then there are security purpose surveillance drones. Second application we see from the drone industry is in the agricultural field, where we can reduce the man effort in doing the tedious agricultural work, and kind of automate and reduce the effort for the mankind. And the third use case is to simplify the transportation and supply of the essential goods, whether it's a medical supply or it's a food supply or any other essential supplies that can be performed. The next application seen is for the rescues or fire rescues, or the fire operations can be seen through drones. Drones are widely used in cinematography also, to either to make movies or to make videos, or corporate videos or commercial videos and photography and etc. And next we see the drones used for research purposes underwater, for the Navy applications and other research works. So these are the broad area of applications from the drone. I hope some of your drone would be falling into these categories of applications. Now, let's understand, if your drone comes from a powered engine, so that engine would require the metal parts. Most probably, it may be a stator or rotor, NGV stator rotors or turbine blades from compressor or combustion chamber, or you may require the complete metal frame also. So mostly for the UAVs or for the drones used using these turbojet engines are coming from defense purpose drones, and they have majority of metal parts and carbon fiber parts along with it. Second category, if your drone comes with a IC engine powered, if it is a IC engine powered UAV, then you might most probably require the metal parts again, the typical engine components, cylinder heads, or any other components, pistons and things like that from the engine parts, which are typically made in aluminum material. And then you might find high temperature component also, and few of the plastic part in the engine, which are nylon 12. So from this category, we see majority of the component needed is either on metal or polymer, a few of the polymer components, and a combination of carbon fiber parts as well for the lightweight applications. If your drone comes with battery powered, if your drone is from battery powered drone segment, you might need solutions for battery management systems or batteries, and then fixtures to batteries and fitment, and the frames, of course, the frames of the drones, or enclosures for the drones, or drone mounting. So these are few handpicked examples which are seen already getting manufactured using the 3D printing process. So these examples you can upfront use for your product line, and you can leverage the 3D printing process. From this category, mostly the parts shared are either from polymer or carbon fiber, and few of the metal parts, of course. Now, in order to solve all these challenges in the drone industry, what solutions we have to offer? So from EOS, we have laser powder bed fusion technologies. We have to manufacture the polymer part. We have selective laser sintering process, which is a support structure-free process and a very productive process available in the market, and it's considered one of the industrial production solutions also from the 3D printing segment. And secondly, we have for the metal printing, we have direct metal laser solidification technology with us, which again uses the laser to melt the metal powders. It can melt almost any category of alloys, and give the functional part, whether it is a industrial purpose component or a lightweight component used for the UAV or drone applications. So to begin with, what is a SLS process is, I've taken a video illustration here. We have taken an example of our P3 machine, which has the dispensers on the top. These supplies the powder, and in the middle you see the recorder, which records the powder because it's a powder bed fusion process. And then we have the heaters to preheat the thermoplastic nylon material, and then here the main power unit comes for the curing, which is the laser, which travels through our scanner, and this galvo scanner uh, addresses to all the contours and all the details of the layer we spoke about earlier, that layer information. So this way the laser is able to address all the layered informations one by one, and it begins with zero and then it ends up with the height of the component. And once the printing is over, we take out the exchangeable frame and we unpack our component. So this process is very simple in many ways because it doesn't have hurdles of support structures. It's just deep outing that we have to perform, and our parts are ready. We take the part and directly use it. So this is about SLS process. Now let's understand how the general workflow work for the SLS process. So you have a design model, as I explained earlier, and then you put that design model to the printer, and we print that component. It looks like this, and then that component has to be depowdered. So we have to just finish the component by brushing it or by doing the glass beading. And once that part is finished, we take the part and directly use it for assembly, and we integrate the electronics on it, and then the product is ready. So it is as simple as that. It doesn't need any toolings, or it doesn't need any special curings in between. Depending on on the color or finish, you can choose to color the component through painting or dyes, but this is the natural finish that you get out of it. Now what happens to the powder or the raw material? Why do we call it this is a production method? Because we are able to claim the old powder from the previous build and we are able to reuse it. So the old powder is taken and we save the old powder, and then we take a new powder and refresh the old powder, which is ready for the next use. And this is how we are able to reuse the material in multiple cycles and get the value out of it, which unlike any other 3D printing processes, most of the 3D printing processes do not offer uh, such reusability of the materials. It imparts the sustainability. So right now, with a few of our selective materials, we are able to achieve 80%. We are able to reclaim the 80%, and if we are printing 15 to 20% of the volume out of the quantity that we have taken, so we are ending up with the almost negligible wastages in the process. So since there is very minimum wastage, this process becomes very sustainable once that part is taken out. So this is, for example, we have taken the job, the soft model or the program and the powder for the first use, and we send it to the printer. Printer gives the outcome in the physical part, and the used material is recovered. We see that material and we refresh that material, and we are able to reuse it. So that's how we are able to reclaim the reusability, and this material can be recycled also over the number of users, and that's how it imparts the sustainability in the manufacturing processes. Coming to the software part of it, how do we prepare the data? So the SLS process is one of the simplest process of 3D printing to prepare the data and print the components in a hassle-free manner. We just have to load our datas in the software, and software nowadays are smart enough to auto orient, auto position, and auto place the component in the machine environment. So we just give the command to the software, and it takes care of the positioning of the parts in the way it has to be printed, that we call is the nesting. So with the smart nesting mechanism of the software, this SLS process is ensured to be one of the reliable and most easy process to get your uh, parts printed from 3D printing. So coming to the finish what is the stage when you can use the SLS part? So honestly, you can use the SLS part in any stage. You can take out the part, just depowder it, dedust it, and you use it. It's up to your choice. You can use it in a natural white or black finish part because the thermoplastic nylon materials are available with the monochromatic color options. Either it can be white or black, so we can directly use it in those natural forms, or we have the option to dye them or paint them in variety of colors to use further, and we can integrate it to perform as a functional component for your product. So SLS covers the diversified application needs in any stage of the manufacturing process. There are enormous possibilities with the post processing. So once you get the part, you can do the media blasting. You can use any media like, for example, glass beads to smoothen the outer surface, and you get your finished component. You can do media tumbling, in which you put your part in a ceramic media or any other tumbling media to smoothen the outer surface. And you can also do vapor smoothing of the component in alcoholic base, which smoothens the outer surfaces uh, very promisingly. I'll show you how the finish look like after the vapor smoothing. And next option is, as I said, you can dye the SLS parts in any color. You can go ahead because the base color is white, so you have the option to dye them in any color choices. So this is about possibilities of different surface finishes. This is the standard finish that we have been getting directly from the SLS. This is the surface that which you get. The array value is seen within the range of 7 micron to 8 micron, or sometimes 10 microns also, depending on what orientation you put the part at. But promisingly, it will be within this range after the bead blasting. And then you can further improve the surface finish by doing the polyshot surfacing and deep dye coloring, which are the options available with the company called Dimension. They are giving the solutions, ready-made solutions for the SLS parts, which gets post-processed. And the third option to post-process is the vapor fuse, which gives you utmost packaging on the outermost layer of the plastic part, which are more smoothened, uh, uh, more appealing aesthetically, and then you can go for the dyeing on that part also. You can color them as you wish. So what SLS covers in terms of dimensions, so you can start building from the size of the laser spot that is there. So I'll explain you what laser size we have in our machines is. We start with the 500 micron. Our CO2 lasers in SLS start with 500 micron laser spot dias. So starting from that, it can start printing, start addressing the contour or the part wall thicknesses from that. And this is the illustration. You can see the minimum pin size that is manufacturable through this is 0.6 mm dia, and horizontal walls that we can build with this laser technique is just 300 micron. We can start with that if it is in a horizontal orientation, or in vertical orientation we can start printing at 0.5 mm, which is 500 micron. We also have the fine detail resolution CO lasers with us, which comes with 200 micron dia, and subsequently their end wall thicknesses are half of these wall thicknesses ultimately that you can imagine to print. So this is about the size, what can be printed, and if your component has threads or the requirement to the internal threads or external threads. So external thread, we can start printing from M8 onward, and internal thread, we can always put the thread inserts, the brass thread inserts on the plastic component, because our plastic is thermoplastic and it supports the insertion, thermal insertion and fitment of those inserts, and they're very reliable. So we can always turn around our functional part using these threads options available. Deconstruction of the larger polymer parts. So of course, in 3D printing, there are the build volumes are very limited, or maybe if your component is larger than the build volume, then this concept comes into picture, which is also a design for additive manufacturing. We have to redesign the component during the process. If your component doesn't fit into the build volume, uh, if the design permits for this model to be deconstructed. So we cut the model and then we fit those pieces for printing, which is quite popular and quite usable technique for the components and prototypes in the industry. This way, you can ensure the fitment of the component or subparts of the large component inside the build area of the machine, and then later you can join them using the industrial glues that are available. However, to ensure the best strength of in the joint transitions, there are joining techniques that I'm just displaying before you. So the best results are seen in all three criteria, that are self-alignment and bond area and stress distribution is tongue and groove kind of. So you can always define this joining technique on your large component, and it will help on reducing the shear stress up to certain level, and your parts will be strengthy at the end of the join. And once you paint the component, it won't be reflecting out that it was joined earlier. So this is the way how the bigger components can be manufactured using SLS process. The benefits of SLS process we have seen so far. Let's have a quick look again on what are overall benefits of SLS. Is first, it doesn't need the tooling or any tools for making the parts. So it's a tool-free process. It doesn't require the support structures, unlike any other plastic manufacturing methods or plastic 3D printing methods. The powder is reusable, so this process, this reusability of the powder makes the process more sustainable and more economic and affordable. And this requires minimum post processing on the components because as I mentioned, we can just depowder and start using. It has least of the chemical exposure. The chemical exposure is very less on it, and you can imagine printing the component on the fly, which most of the other 3D printing processes don't offer actually. You can always go in the third dimension, putting as many parts as possible in the available space of the printer. The cost per part for production is very low because of reusability concept of the powders, and the laser processes is anyway much faster than any other 3D printing, which gives the highest throughput out of it. We are having the glass filled material, we are having composite materials, carbon compounded composite materials, we have flame retardant materials with us. This SLS process don't require any post curing, so the cycle to manufacture or time to manufacture is very minimum, and it doesn't have much of most of the materials from SLS don't have UV damage. Literally, over the period of time, you don't experience any UV damage on these materials, so they are very reliable. And you can always manufacture the parts which are with the suitable functionality, and you can test them for as per your requirement. And as I said, the functional thread manufacturing is also possible. It can print very minute parts with the details starting from 200 micron with our FDR laser, and normal 500 micron with our normal CO2 laser. And part deconstruction is possible. If the part is literally very large or very big, you can deconstruct and make it and join it later. The components are watertight. with the 2 wall thickness onward. So these are all benefits that are there with the SLS process. Now let's look into the DMLS process. What is DMLS? It's basically a metal printing technique, which is again a laser powder bed fusion, which uses the powder and the laser source to melt the material, and then these parts are melted on top of a substrate plate, and it happens in an inert atmosphere. You can have any alloy printing possible with the DMLS, whether it is aluminum alloy or inconel alloy, super alloys, or titanium, like with titanium alloys, copper. So today we have more than 40 to 45 alloys already proven in our machines, and there are new alloys getting developed every day through our machines. Our users are using machines for innovating new materials, because this machine supports the third party material, and you can always try out the new materials and fuse them using the laser source. So this process again very simple. It recoats the powder in the layer thickness of starting from 20 micron to 60 micron or 90 micron, depending on the requirement. And once the coating is done, the laser addresses those 2D layer informations, and once the printing is over, again we depowder and we take out the part, put it in a furnace for the stress relieving, remove the support structures. Middle process, DMLS process, comes with the support structures, of course, and those need to be removed after the stress relieving process. And after that, we can choose what amount of post processing we need to do on the part, whether we need to do machining, EDM, wire cut, and polishing. All of these processes are supported by our 3D printed materials. So this is about how DMLS process works, starting from powder form to the final component. So the general workflow of DMLS technology, if you want to understand, I've taken an example of a cylinder head here. You have an input in the CAD data form, and then we have to take that CAD data into the data preparation software. It can be a Magic software, or maybe a NetFab software. We do the orientation of the part in metal. Uh, Most of the time, the metal orientations are preferred to be manual, with the experienced application engineers, because it requires the attention for the heat transfer and other complexities in the metal printing. So uh, and that is addressable using the different softwares again. And in the data preparation, we do orientation, we define the support structure that support the processes, support the material, and also work as a heat transfer media. And once the data preparation is done, we slice it and send that information to the printer. Printer addresses to those layers and details, scanning and melting it, that we call DMLS. And after the printing is over, we take out the build, as I mentioned, and we put it in a furnace for stress relieving, and we remove the support and do the other kind of post processing, like short blasting, or we may go for machining depending on the requirement, and we get the final finished component. So this is about DMLS, how you get the middle part out of the digital data that we have. Okay, so this is about the manufacturing solutions that we have to offer. Now let's have a look into what all polymer materials that we have in SLS. So we have nylon 11, we have nylon 12, different other grades, subgrades of nylon 11, nylon 12. In nylon 12, we have glass fill material, we have FR material with us, flame retardant material tested for many other applications you can use for your drone applications, where flame operations or operations are intention, or if you want to use it for your battery pack, you can opt for it. And then we have newly launched PA950 HD, which comes with its highest reusability. It is reusable 80%, so we'll talk about it later. And then we have composite, the polymer and metal composite, which is alumide. It's a mixture of nylon 12 and aluminum. And we have flexible material, which is thermoplastic urethane 1301, We have carbon filled material PA640 GSLs, and both PA11 and PA12 we have carbon fiber material which can be used by the drone industry. We'll talk in detail about it. So these are all broad material list that we use for the SLS. To begin with, our first material very much suitable for drone application is P11 based HP1130 material, which is a high performance material. It's a carbon fiber filled material which has a high impact resistance and high strength and stiffness with it. It has a superior thermal properties as well. And this as a basic composition or basic polymer. It is a melt compounded carbon fiber, which has the carbon particle melted in it and then compounded. So at the end of the day, when you fuse your part, when you fuse your uh, powder into the physical part, you get more promising properties along with the carbon particles that are there, which are superior, or I would say better than the other carbon fiber composite materials available in the 3D printing industry. And they are quite isotropic in XY orientation. When we print the actual part, you can see the mechanical strength here. In the XY, these parts are at 556 MPa, and in Z they are 46 MPa. And these materials are highly reusable again. 80% of the material can be reused. We have flame retardant material, which is FR106, again PA11 based flame retardant material. It has a high impact strength, and it is tested and complied under FAR 25.853, which is a vertical burning test. And the application for this materials are automotive, and it can be used in automotive, in drone, in aviations, and interior components of the aviation industry. So, what is the application with the flame retardant material? I have taken an example here where people have used polyamide 12 based material. This is not exactly a flame retardant material, but flame retardant material will perform better than this because this is the natural polyamide 12 material they have used it, and they have literally put it at 200 degrees temperature, send a drone to check how it is able to protect the internal electronics and internal components of the drone. So with the FR material, you can expect more protection than the normal than our normal polyamide 12 material. We have another carbon fiber material, which is PA640 GSL. It is a PA12 based material again, nylon 12, and it's a carbon fiber. It's a mixture of uh, carbon fiber and hollow glass beads filled. And the best part of this material is with the same amount of strength, mechanical strength, it is 10% lighter than the other available plastic material in the market. So it offers another 10% of the advantage to your drone design, and you can imagine more endurance of your drone when it is running because the flight ratio is increased and strength to weight ratio is also increased with it. It is easy to process and it gives excellent surface finish. Is available in matte gray color and matte black gray color, I would say, uh, in appearance. We have, as I said, the new material with us in our portfolio in SLS, which is LMP 950 HD, which is high definition, comes in black color. This nylon 12 material comes up with 35% less total cost of ownership, and it is 80% reusable. So we can expect least wastages when we print our part out of this process and using this material. It gives a super surface quality with excellent touch and feel and minimized post processing, and it is optimized with the TCO balancing material use rate and packing density. Then, with our new systems, we have improved the performance of our existing PA 2200 material, which is earlier it used to be 50-50%. Now with the new systems, we are able to use 70% old material and 30% new material, which is a great win for the regular users of nylon 12 material. And carbon footprint is also decreased with the new offerings of nylon 12 material. Okay, so this is it about polymer materials to that we have to offer. Now we'll jump into the metal material. So metal material, we have lightweight aluminum alloys, different aluminum alloys with us, and then we have lightweight titanium alloys to offer. The titanium can be used in different areas of drones. It can be used for a structural component. It can be used for fixtures or any other metal component because it is literally half of the steel in terms of density and with a great strength is offered with a great fatigue life and a strength with it. Then we have super alloys for the applications like mini turbojet engines where temperatures are very high. So we have Inconel 718, 625, 939, and Hestalloy. We also have copper to offer for heat sink applications and other temperature applications. We have copper alloys as well as pure copper with us. We have cobalt chrome MP1, and we have different stainless steels and high strength steels also, if in case any requirement is there from the process side or from the production side. So this is about the high temperature applications in kernel 718 that I talked about. So we have in kernel 718, which has a maximum service temperature in the range of 700 degrees. Then we have 625 in the range of 800 degrees. We have Heinz 2, 82, and we have 939, which is in between 850 to 900. And we have other Hestalloy, which is close to the 1100 degrees. So these are all our high temperature metal alloys that are super alloys that are available with the 3D printing, metal 3D printing process. Now we'll have a look into what is designed for additive manufacturing. So before I jump into this topic, I will like to explain people in industry take the design for additive manufacturing and typical perceptions, but design for additive manufacturing can be any simplified process, or I would say the process in 3D printing which solves your problem. So what problems it can solve is we call it objective, or if we say what is the design for additive manufacturing. So design for additive manufacturing is used for 3D printing process simplification such as support structure optimization. So we can look at different kinds of support structures and typically used in metal 3D printing processes. We have various kinds of support structures now optimized in the industry, which solves the problem of 3D printing. And we can look at part orientation as again a part of design for additive manufacturing. What we are aiming for the part orientation, whether our aim is to get the good quality or get the lowest cost, that synergy. And then geometry modification to reduce support structures. So sometime because it's a layer-wise process, so we have to simplify the geometry in such a way that it supports the component building using the 3D printing. So we can think of modifying the geometry in most of the self-supporting reasons. Self-supporting reason I mean to say is it doesn't require the support structures, especially for metal 3D printing. So that is one of the purpose or objective for the DFAM. And we can also use the DFAM for complete re-engineering of the component for enhancing its performance or solving any of the industrial problems. So we can do a complete re-engineering of the component starting from design to manufacturing. And then, of course, one of the popular DFAM tactic or technique is topology optimization, where we always aim to reduce the mass of the design or mass of the component and lightweight it, and assembly simplification, where we aim for simplifying the assembly and reduce the part count. And design integration with lightweight multi-skill structure. This is quite popular in few of the industries like medical industry, and of course it can be used in drone industry where you can integrate the lattice structures or different other structures like gyroid structure is used for heat dissipation applications and most of the heat exchangers. So there are several other lightweight multi-scale structures which can be integrated into the mechanical part and then reduce the weight in it. And we can also apply the design for additive manufacturing driven by the material. So if we are developing some component with the alternate material, so we can always redefine the design boundaries with respect to the material mechanical strength that is available or what we are targeting and what we are using for the 3D printing. And what outcome we get out of applying these DFAM tactics? We get the cost optimization. So most of the time, our focus is to reduce the cost more and more. And we always prefer quality to be enhanced in any stages. So we try and reducing the effort that is taken in the 3D printing process. We try to reduce the cycle time of 3D printing always by using the DFAM and performance enhancement of the component. So end goal of applying the DFAM in the component is that it should function and perform qualitatively and up to mark that we have to ensure using the DFAM. So that is the outcome, and improved strength to weight ratio, of course, by using topology optimization or by using the lightweight materials in the process, we can look at improving the strength to weight ratio of the actual component. So, and the next outcome is simplified AM process chain. Of course, if we are redesigning the component with respect to the environment of 3D printing and we are aiming for a batch production through 3D printing, we can of course simplify the complete production process chain with respect to the 3D printing process, and we can target a cost, we can target the number of parts per cycle, and we can simplify the process chain using the 3D printing, and the 3D printing will become the production process for that. So what is topology optimization? So here I've taken an example of a sheet metal part which has multiple parts, and then it is integrated into one assembly. It is 40% lighter, 20% stronger in terms of the material and the processes used in this. I've taken another example from the chassis, which is originally a sheet metal part, but it is topologically optimized and it is 15% lighter with the factor of safety 1.2%. So for a typical sheet metal component, we can always aim minimum 15% to at least 40%, depending on what component we are choosing for optimization. But we can always look at optimizing the designs using topology optimization, and it will be reducing the effort taken by 3D printing ultimately if we are not choosing the conventional design. One more example I have taken from the drone industry itself for the design for additive manufacturing. So a drone typically has mechanical components, structures, and fasteners, and the electrical components, GPS module, battery, and rotors, of course, and the engine controllers. So this example has part list of support frame, which is of aluminum, and beam carbon plus wood, and a ring which is elastic, and the mounting plates and screws and fasteners, things like this are there in the electronic element. Then if we look at the structural element of it, we have mounting plates and mounting plate top and bottom, support frames, and other ring elements, of course. So our aim is to observe what are the drawbacks of the conventional design. So advantage of conventional design is, of course, the material cost is cheaper uh, to procure, and electronics, standard electronics are designed for that and meant for that, but it doesn't offer most of the protections because they have large number of parts. Conventional drone have large number of parts. They are having more weight and lead time is more because each and every part has to go through a different manufacturing process. The electronics are unprotected most of the time unless it is not simplified. The design is not simplified, and if you go with the primitive design and limited innovations and customization is available because of the challenges of forming. So how do we address all of these is by if we want to shorten the time of development and optimize it, we take that old design model and we go for the form finding, and then we do the uh, boundary condition analysis, FE analysis, and then start remodeling, getting the different shapes for possible shapes, considering the factors like part integration for payloads, multiple parts, and complex geometries for aerodynamic and shape, and functional integration of the electronics, and of course customization can be integrated. So encountering all these criterias, we can choose among these different shapes available in the iterative method of topology optimization, and then we can leverage it into the drone industry. So the main advantage here is you don't have multiple parts, you don't have to deal with multiple parts. Your electronics is more protected when you integrate it finally. The economic value proposition, if we talk about it, we have taken an example with our P3 system. With such an example of 273 centimeter part and 76 height part or the frame. In one cycle, we are able to get 9 sets of the drone and various other propellers along with it. So this is an example of that how of the cycle or of the build, how we can leverage multiple parts per cycle. And the benchmark quantity for this is 216 parts per month, and you can look at 2,592 parts per year with the size of this drone with one machine. And this is not where it will stop. You can, we have now a new system which is more productive. So this is the illustration from the old system. We have reassessed it, and this is the illustration from the new system, which is our P3 next generation model, which is P3 next. And you can see how many parts are packed here. We have increased the productivity by 39% compared to the previous model for this example. And overall, the machine's productivity is also increased by 50%. So we'll talk about it later, but this is the example in terms of the value proposition with the new system. The other value proposition is the large number of parts have been reduced from 41 to 27. The weight is reduced by the topology optimization. The lead time is reduced. The innovations have imparted. The customization is possible now. You can look at varying the thicknesses as per your requirement internally. You can make the frame hollow also, and you can use it for different purposes altogether. So there is high amount of customization, whether it is for fitment of the electronics or any other component in the uh, redesigned frame. So this is the transition from the conventional manufacturing to AM manufacturing. This is the old design, and this is what we have got the new and redesigned model by applying the DFAM. And this is how the parts is manufactured. So this is the normal layout. We print the part, we take them to the unpacking station, and then we do depowdering and get the parts. So this is the natural outcome, and then we dye the component, and this is the final finish. And after the integration of the assembly, this is how the final product look like. So that's how we can apply the DFAM techniques to manufacture the drone parts and simplify the designs. I'll jump to the few of the case studies here. So this is one drone bird case study from a falcon. This drone bird is used for getting the birds away from the airfield in some of the airport. This is being used, and this is manufactured using the nylon 12 composite material, which I mentioned, PA640 GSL. It is a lightweight carbon material. It resulted as a faster delivery time, lower production cost, and versatile in shape. Overall, this drone bird is 750 gram in weight, and and it is 15 minute. Uh, it is giving the endurance of 15 minutes. It can do the maneuvers of the real bird, and it can mimic the motions of the real bird, which is used for distracting and getting the birds away of the airfield used in airport. And this is a very good example where we can think out of the box in terms of designing, applying different DFAM techniques to manufacture the drone components. And yeah, so just skip this. Coming to the next case study, which is from defense. This is the scale down design again from the UAV. Complete structure is manufactured using the aluminum, you can see here, and most of the other components are also 3D printed. So 3D printing is solving a lot of industrial problems and challenges, in whether it is from the enterprise drone segment or from the defense drone segments. This is one more example of titanium frame printed through our system. Uh, this first got redesigned, and then they were produced using our M400 system and got successfully installed. This is one more case study from the uh, APL engineers. It's a it's a Crackus It's a Crackus drone, which is corrosion-resistant aerial covert unmanned nautical system. It is used for uh, underwater research and underwater surveillance purpose, and it can fly several feet down the water, and it can also fly above the water level in the air. This is used for carrying the load and for naval application. The challenge for this drone was to make it corrosive resistant, keep it corrosive resistant in a very rugged environment, especially humid environment. So the challenge was to keep most of the component dry, and they were successfully able to address all those problems using the EOS SLS solution, SLS process. They printed it in nylon 12 material, and then uh, most of the electronics and other components were packed, and only exposed component, which are motors, they coated it with the industrial coatings available, waterproof coating, and they put it underwater for 2 months, and they saw no evidences of corrosion due to water. So this is a great example how 3D printing is helping most of the industrial applications in drone. Okay, we'll come to our last topic of the webinar, which is cost analysis. I'll not take much time for this. So as I've been explaining, what is 3D printing is, you have a material and then you are adding that material to form the shape, and you're ending with least of the wastage available. So what are the different cost factors that are responsible uh, for getting the cost of the component? So first factor is the raw material. So raw material gets used on the actual part, and then raw material wasted in the processing of the powder, and the material wasted in the support structure. So in our SLS case, the support structure is not used, so we don't waste on that area, which is about 20 to 30%, starting from 30% to sometimes 60, 70% also, depending on the geometry that we are printing. So that is the first factor. And then second factor, which has the most weightage in the cost, is the printing process. And the third factor is the post processing and other things like packaging or forwarding or any other processing on the component. So there are two major factors. And if we look at the graph of the conventional or traditional manufacturing between unit cost and output versus the 3D printed, so you can see uh, conventionally, the process takes most of the investment, and then you get your payback over the period of time and uses of your investment. You leverage that investment, and in 3D printing process, the curve is quite steep and going slightly down because of the optimization in the processes. And if we merge both of them, this is what we get, which we call break-even point. So this is the point before which the 3D printing has a sweet spot. So up to this point, whatever output or whatever quantity we are getting, they are always less costly compared to traditional methods. Now let's understand uh, why this 3D printing process is steep, because our processes, machine processes, are quite identical. We don't change much once we do the first batches or few first batches. After that, most of the processes are very constant. And then there is a material cost, which is anyway constant. So if we are able to reduce the material cost somehow by simplifying the material cost, and if we are using the advanced multi-ledger systems or advanced systems, parameter system, then we will be able to drop this 3D printing curve down. And this is what the result will look like. So with as I said, with our new system, we have increased our productivity by 50%, which is P3 Next, by by improving on the processes. And from this to this, we have achieved so first, reducing the time in our pre-processing, we have cut down the time from 120 minutes to 80 minutes, and of the preheating. And then in building process, we have reduced by 36%, and in post cooling, we have reduced by 90%. So overall, we have increased the productivity 50%, and machines availability is guaranteed at 90%. So now you can imagine to use this machine almost every day for your day-to-day production purpose. And this is where I have taken example of different production scenarios and costing. So in the first scenario, which is the example of the prototyping, and second scenario is the batch production, and these are the mass production using 3D printing. You can imagine if you have the equipment in house to print 1 cc component, 1 cc of the plastic material, the basic nylon. It may range from 15 rupees to 20 rupees, depending on how you are handling the powder and how you're managing powder. The commercial, I have taken an example of the commercial calculation for our P110 machine, which is in one cycle taking 104 parts, completing the cycle within 15 hours. So such kind of build with our P110 machine, you can imagine everyday cycle from Monday to Friday or Monday to Saturday. And the outcome of this is cost per part is 350 rupees per part. And this can even further optimize by optimizing the powder reuses. One more example on metal, not only on polymer, but in metal also, we have simplified process parameters where we are able to print in the third dimension. Like for example, with our production machine 300-41 kilowatt, we have taken one example of the IC engine cylinder block, which there are 36 total number of 36 cylinder heads which are printed in one go. This is possible with the help of our 5x increased productivity by the quad laser, which is increased from 200 gram per hour to print 1000 gram per hour. So this results just one cylinder per hour with the cost almost equivalent to the pressure die casting cost. So there are techniques which we are implementing in our EOS portfolios to improve the cost. And we also have web-based software to offer for cost analysis, which will help you on your design optimization and to prepare the commercial reports and prepare the cost comparison reports. These are the machines which we have to offer. These all are from Polymer, P110, P3 Next, P770, and these are our metal systems which you can anyway contact us to set up for you and build the production system. So I'll jump.
Okay, Arun. Thank you. Thank you for such a informative session. Now we are at the end of
Thank
our
you.
webinar. So now I would like to thank Arun for delivering a very insightful webinar today. I am very confident it was very helpful for our audience today. I also would like to thank our audience for taking their time out and joining this session. If you have any queries related to the subject matter or any other requirements, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us at any time and we would be happy to address your queries. Please do keep an eye on our upcoming seminars and webinars. So you can follow us on our social media platform for the same. Thank you, everyone.
Thank you. Good day.